In this tutorial, we're going to discuss how to calculate the standard electromotive force, otherwise known as EMF, of a wet cell battery. This standard EMF is also called cell potential, or E naught. And this naught symbol is what tells us that we are under standard conditions. Standard conditions are 1 molar concentration of our solutions or 1 atmosphere of pressure of a gas. So if you are operating under standard conditions, the equation and the process that we're going to discuss in this video would apply. If you are operating under non-standard conditions, anytime your concentration wavers from this 1 molar or your pressure is no longer 1 atmosphere, you have to calculate the cell EMF or cell potential under non-standard conditions, and there will be a different video on that. So this is basically what a wet cell battery looks like. The batteries you're used to seeing in a watch or a flashlight are called dry cells, and that's because any of the moisture content is much more minimal than what you see here in these two beakers, in these two solutions, and that moisture is typically in the center of the cell. But those are called dry cells, and these are wet cells for obvious reasons. And what we have here are two solutions in which there would be probably a salt or some sort of an acid like HCl, and it would ionize and dissociate to form ions, and those ions of course would carry electrical charge. And we have two nodes in which this electrical potential difference is calculated. We have the cathode and we have the anode. The cathode is the reduction half, and the anode is where the oxidation half takes place. So this is what a typical wet cell would look like. And in this particular beaker, the left half is typically going to be our anode, and in the right we would have our cathode. An anode is where oxidation takes place, and cathode is where the reduction takes place. And this little segment is called our salt bridge. This is typically a tube that extends from both into both beakers, and that is where electron flow can occur. And the electron flow occurs from the anode and into the cathode. That is how electrons are lost in the oxidation process and gained into the cathode in the reduction process. This is what a typical wet cell would look like. And of course the number of electrons is based on however many electrons the anode chooses to lose and the cathode chooses to gain, but these electron numbers should always be equal. So that being said, let's take a look at an example of, let's say, a magnesium containing salt and a copper containing salt. And in order to determine, okay, well, what is going to be in the anode and what is going to be in the cathode, we would have to look up the E naught values for each of these particular atoms. And those values can typically be found on a reference table of sorts. So the standard cell potential that we are going to be calculating must come from these values. So the E naught for magnesium is actually negative 2.37 volts, and that for copper is positive 0.34 volts. And knowing the difference between these two electrical potentials is what's going to be captured or measured in a voltmeter somewhere up here. How many volts of electrical current or potential are going to be produced from this process? So how do we know which of these was the cathode and which one was the anode, meaning which one was reduced and which one was oxidized? Well, there is a trend that the more positive the E naught of your cell, the more likely it is to be reduced. That means if this is more positive, the copper is most likely to be reduced. The more negative, therefore, should be oxidized. That means our magnesium, therefore, is our anode, and our copper is our cathode. So, our anode, the oxidation half, this is going to be where our magnesium is, and it is going to become magnesium 2+ by giving off 2 electrons, which are gained over here into the cathode, the reduction half, and that is where the copper is going to be. This is copper. So magnesium becomes magnesium 2+, and copper becomes neutral copper. All right, now that we have established what is going where, we're going to write our two half reactions of the equation just to be sure. And that means that if magnesium starts off as a neutral solid magnesium, it will turn into magnesium 2+ by becoming oxidized and releasing 2 electrons. That is the oxidation half. The reduction half would mean that copper was a 2+ aqueous ion, and it became copper solid that's neutral. How did that happen? It gained these 2 electrons. So those are our two half reactions. We can look those up in the table, and that is how we can attain those values. We have identified what is going to be oxidized and what is the anode, and that is, of course, our magnesium. We have identified what is going to be reduced, which will act as our cathode, and that is our copper. And we have the values that coordinate with that. So what values do we have here? We have the values of magnesium is negative 2.37 and copper is positive 0.34. And these values are just strictly plucked right out of the standard reduction potentials table. You should not change these signs under any circumstance when using this equation. Yes, the charges are reversed in a reverse process, meaning these values represent reductions, which is true for copper. But for magnesium, magnesium is not being reduced, it's being oxidized. So this should actually be a positive charge if we reverse the reaction. But we're not going to reverse this negative sign. It should be reversed into a positive because this is not a reduction value anymore, it's an oxidation value, but we're not going to be doing that. The equation will do that for us. So let me illustrate. We're asked to calculate the standard EMF of a cell that uses magnesium and copper half cell reactions, which is what we have. How are we going to do that? We're going to use this equation right here. The E naught of the cell is equal to the E of the cathode minus the E naught of the anode, right? So E naught of the cell equals the E naught. What is our cathode? That is our copper, minus the E naught of our anode, which is our magnesium. How do we calculate that? E naught of the cell equals E naught of the copper is 0.34 volts minus the E naught of our magnesium, which is negative 2.37 volts. All right, let's see what happens. Remember, what we're trying to do is reverse the sign here of this magnesium, but we're not going to do it. The equation will if we've set everything up correctly. A negative and the negative makes a positive, and there's the change of sign. Again, we didn't do that, the equation did. So 0.34 volts plus 2.37 volts is a total of positive 2.71 volts. So what would this voltmeter have read up here? This would have read 2.71 volts being run when the oxidation reduction reaction here occurs. So follow these steps, grab your values, and then make sure that you have assigned the proper node to the proper atom, and it's as simple as plugging into our equation.